Thank you so much for the kind introduction, and thank you all for being here. So welcome. As said, I am a PhD student. I have been working on property-based testing for 4 years now, and I really like it. So I have some objectives throughout my talk, and the last one is to get you to like it. The first two are, I hope that after getting out of this room, everybody knows what property-based testing is, and at least the majority has some idea of how they could use it in their own work, and at least some of you would like to use it after this. So throughout the talk, I'm first going to give some overview of what property-based testing is. Stefan already did that in the previous session. If you have seen that, there's going to be some overlap, but I will be focusing on, fortunately, a different part of property-based testing, in mostly, which are properties themselves. And the second and kind of a long part of the talk is going to have a lot of examples, and these are going to have a lot of code. And this code is going to be in Python. So I know this has been a long day. I know everybody, including me, is tired. So you may have trouble following at any point. Please just stop me and ask. That is OK. So because I want everybody to be able to understand that as much as possible. And then I'm very passionate about property-based testing. There are a lot of things that I will not have time to talk about. So I will have this very fast one slide that has all the things that you might want to check out if this talk is interesting to you. So in a better world, we might not have had to write tests, but we do not live in that world, right? So all of us write some tests in some form, and although the most common form is just example-based unit test, I'm sure a lot of you, even if you have not used property-based testing itself, have used some type of random testing. It could be running a fuzzer in the CI, or any type of testing that automates the things that your program does. So what is property-based testing is throwing back to the original paper. It is a lightweight mechanism. It's a lightweight tool for random testing programs. And to me, it has two components when you look at it from a very high level. The first one is, of course, random generation. You want to be able to somehow pick elements from the state space of your program. And the second is what we call executable specifications. And they look very cool, but they are plain properties at the end. So they are the main object that when we are doing property-based testing, work around, talk about, try to understand, and craft. So what I like to do when talking about properties is start from an example-based test and abstract my way back to a property. So an example-based test here is an executable specification over some concrete inputs. So here we see a unit test of a list append function, right? We create a list, we append an element, and we have an expectation of what the end list looks like. So we write that. And yeah, so as I said, everything is going to be using Python. And I will be using the main PBT framework in Python, Hypothesis. It's a very nice framework. So if there is anything that looks unfamiliar to you, just ask. So let's start from this example, right? And the first thing that I will be doing is I will remove the hidden L from the assertion at the end, right? Because the 1, 2, 3 at the prefix of the list, that is actually part of the L. So I just removed it to make it into this assert for an L, which is one possible abstraction of that specific assertion. So the second thing I do, this is a much bigger jump. Now I abstract L itself. Before here, I had L as a concrete list. Now I'm talking about any list, right? And this list, when I'm talking about this list, I'm using this given decorator. It is a function that Hypothesis gives us. And it means that this is the hypothesis test. So when I run this, hypothesis is going to take the expression inside the given decorator, and that expression is a generator. Hypothesis knows that, so it's going to sample that generator. So what we see there is we see a generator for a lists of integers. So now the semantics of running this is I'll generate a random L, then I'm going to append 4 to it, then I'm going to check if the 4 is in the list at the end. And the last step of abstraction we do is we now generate x2. Before we were using a concrete 4, but now our property is somewhat fully abstracted away, right? So going back to our example-based test, I made this like very simple utility, so we can write these tests in a very concise manner in one-liners. So our first property-based test, it looked something like this when we were writing it. It is represented, like when you think about it mathematically, it is represented as the following proposition. It says that for all lists and x's, x should be in append lx, the expression. So there are other properties such as this is a stronger version of the containment property, right? I'm not saying that the list contains the element. I'm giving the specific position of the element in the list. Are there any other example like properties that you can think of that could arise here? Anyone?
Length is one larger than before.
That is one. There is one more. Yes.
The rest of the list should be
Yeah. So those are the two. Okay. So a property now is an executable specification of a program over some abstract set of inputs, right? And that is what we did. We took some concrete inputs and we changed the executable specification we had to make it an abstract version of it. So some other properties that you might have already realized or encountered in some form as idempotency is a very important one. We see it a lot. That means that when you apply a function twice on something, the result is the same as applying it once. So sorting is an idempotent operation. And the classic example that also exists in the original QuickCheck is reversing a function, like reversing a list twice gives you back the original function. And what I will do now is I will give you a sorted list, sorted list data structure, and then we are going to talk about 4 different types of properties that you can, and we will be showing concrete examples of those and how we can write them on sorted lists. And a sorted list, like as the name implies, it is a list with the invariant that its elements are always sorted. So this is how you create it. If you give it any list, it sorts the elements. And if you try to add an element to it, it does a linear scan. It finds the point that it needs to put the element. That it inserts it to the list that it maintains inside it. There is an isSorted function so that we can check the invariant ourselves, which just checks like monotonicity in the list. There is a delete, which uses the find, and the find is just a binary search, and delete finds the element, and if it exists, it just removes it. So here we see a sketch of a generator for sorted lists. Before we saw generators for lists and integers. They were already given to us by hypothesis. So how do we write one ourselves is the question. And the composite here tells hypothesis that this is the generator that's going to sample other generators and construct a new generator. And the sampling operation is done by the draw function that we have. So whenever you see a draw inside the function here, it is going to be an abstract operation that randomly picks something from that generator. So one possible generator that we could write for this type is we could just generate a random list, and then we could give it to the sorted list constructor because it already sorts it, right? But that is boring, so we'll do one from scratch. So what we do here is we first start with an empty list of values. So this is just a plain list, and we randomly generate a lower bound. This could be -1, 42,000, anything else. So then we decide on the length of the list, again randomly, between 0 and 100. And then for each element now that we want to add to the list, we pick an element that is greater than or equal to the current lower bound. We update the lower bound because we know that the element is always going to be non-strictly increasing, and then we append the element to the list that we maintained. And at the end of this for loop, we know that the list we have is sorted. So we can just use that to construct a sorted list. So we create a sorted list, we swap the values, and then we return it. So this is how you can write, this is the style that we write generators in. We compose these different randomnesses together to construct one larger structure. Any questions so far? Anything that's like I moved too fast or something like that? Okay. So I'm now going to talk about, as I said, 4 different types of properties. I luckily didn't invent these. Like they are not just figments of my imagination. They are taken from an article on writing, like a guide to writing properties for pure functions. It's written by John Hughes, the inventor of QuickCheck. And the first one is validity testing. So if you have a data structure or an algorithm or a class, and you know you have a validity predicate on that, which is like in a sorted list, it's sortedness. In a binary search list, it is the invariant that everything to the left is smaller and everything to the right is greater than you, and so on. So when we have a sorted list like this, we know that any operation that we can apply on top of it should result in sorted lists again. And we can informally state it as here, every insert delete on a sorted list should result in a sorted list. And if we were to write it as a hypothesis test, this is how we would write it. Because we now define sorted lists, we can use it in the given as one of our generators. So we generate a sorted list and an integer, and then we insert it, check if the result is sorted, and then we delete it, we check if the result is sorted. So a second type of property is post-condition testing. So you have some predicate that you think should hold after the operation. So this is actually these things are I call them types, but they are much more like styles of thinking about properties. So almost all of the validity conditions they can be thought of as post conditions because you do some operation and then you check it. So yeah, but they are much more this one is much more general. You can have any predicate here. So one predicate that I have is inserted value should be in the list. We had already written this before, right? It is the same property that we had for lists. A third one is called metamorphic testing. And this means that you have 2 different operations or 2 distinct operations, and they have some relation with each other. So here what I have is, it doesn't matter if I insert 2 or 5, or like 2 then 5 or 5 then 2, because the insertion order in a sorted list is irrelevant, right? So this is how I would write it. So insert x and y is equal to insert y then x. And the last one is called model testing. So in model testing, you have 2 things that you know should behave the same. Typically, one of these things is more abstract or simple or naive than the other, or it's more mathematically correct or perhaps it's your legacy system that you're replacing. So the example that I will be showing here is our sorted list has some operations that you have on lists very fast, right? Finding max is 01 because you just check the last element. Finding min is 01 because you just check the first element. And the find operation should, of course, like, even though it's like the list uses a linear scan and the sorted list uses a binary search, they should always give the same result. For this, if the when the list is a permutation of the sorted list. So if we were to write this as a test in a hypothesis again, we would generate list of integers first. Then we would create a sorted list out of those. And if there are no elements, then there should be no elements in the other one too. Then we just check these three. And just like one very minor quality of life improvement, if you care to use hypothesis someday, if you already have typeends and if you registered your generators, then you don't need to write the given, you don't need to write them into the given. It can infer it. Whew. So so far what we have talked about is like kind of, it has been abstract. So now in this page I will give you some properties that they are canonical, basically. They are properties that we see in different domains again and again and again. So it is very likely that they will be useful to you somehow. And the first one is the round trip property. So it typically arises when you're serializing and then deserializing something, and you want to go back, right? Like this is like if you have a lossless compression, then compressing and decompressing your data should yield the same result. And like this is the only JavaScript part in the talk. I already talked about idempotency. This especially arises in distributed systems because you don't get the guarantee that messages are delivered only once sometimes, but you need them to be processed only once. So you want your system to be idempotent. Class invariants, we have already talked about them. And as Stefan talked in his talk, fast testing is a type of property. It is the property that your program does not crash. So we can always use that. And differential testing is like, it's very much in line with model testing. You have two things, you expect them to be the same, right? So this is very useful when you can implement something naive, small and slow, and then you implement a much more complex and production grade version of something. So let's go into a case study. Like the next 10 or ish minutes is going to be about key value stores. We all know key value stores. We use them every day. And one thing that is really nice about them is they are ubiquitous, right? We have like key value stores as dictionaries in Python that we all use, or objects in JavaScript. But we also have them as these like very complex systems that's distributed through like thousands of nodes. And they basically have the same underlying interface. You put something in, then you get something out. So in this example that I implemented, we have a single store, like a single server, that is the store. And then we have multiple clients that can interact with it at the same time. So there is a very simple interface when a client wants to talk to a store. They can send these queries, which could be, they could put an item inside, and they could get the item that they put. There is also one, like they can also delete it, but there is also this select query. And what this query allows them to do is get a bunch of items back that respects a given regex. So what this gives you, when Bob sends this here, they are going to get like Bob _a for. This is the like whole record that's being stored in the database, and that is because this specific store implements the isolation between different clients using this prefixing mechanism. So my name is Alp. Anything that I send to the send to the store is going to be prefixed with Alp, and for Bob, that is Bob. So there are two round-trip properties that I have been able to devise when implementing this. I would like you to guess them, or like perhaps outdo me and like find properties that I couldn't think of.
Insert?
Hmm?
Insert? If you insert the same value twice,
Yeah. So what that is, but that is not a round trip property, right? Like that is a
Oh, I was thinking about idempotency.
yeah.
Sorry.
Yeah, like that also works. I didn't think of that. Anyone else? Yes.
If you insert and then delete the same element, you should get the same thing.
Yeah, that works. Any other? Okay, I'll just move on. Yes. So one thing is, typically when you're implementing a storage, you have some like persistence option. You want to be able to save it. So if I save the database and then load it back, I should get the same store. It should its behavior should be as if I did not save and load it. And another one, which I actually found a bug in my own implementation when implementing this, is message serialization and deserialization, right? So when I as the client want to send a message, I serialize that message, I send it over the wire, and server deconstructs that message by deserializing it, and they have to be the same message. If the server cannot deserialize it, then I may as well have not sent it before. So this is the property test that I wrote. So I have a generator called messages that I'll be showing you in a minute. So that generates a message, and that gets serialized, deserialized back, and I check that both of them are the same. So this was the implementation that I was using. So here we see the insert, like an insert that is like for key foo, it inserts this like object that is bar 42 into the store, right? And the first thing I do is I treat it as if it's this table with types and data. So, and what the deserialization does is, so you see here how I write it, right? Like I write the type, then there is this like \r\n, which is the separator between the type and the data, and each row here is separated by like two new lines. So yes, there is a bug here. Can anyone spot it with looking? If you were writing a unit test, could you? No, like that's okay, because I should have shown that. I deleted that. I had that slide. The way I it's a shortcut. The way I serialize an object is I just print it in Python, and the way I deserialize it back is just I eval it. So that is a huge thing no one should ever do, because like somebody could just do remote code execution on my code, but that's okay. So the way I deserialize this is I first split it by each row. Then for each row, I split it by the -r-n in the beginning. Can you see what's happening? Yes?
If the value contains those characters.
Yeah. If the value contains those characters, or if the value ends or begins with a new line. Because what happens in that case is, so you see here, this is the actual separator for for this thing, right? But I see this before that. So the split is going to think this is the separator, and the type is going to be \n null, which doesn't exist. So that's what happens. And here we have like this -n, which separates string, and like -n, like this illegible string. But what happens is because -n, like \n gets parsed first, it thinks that like there is a string r, which is a like type and some data, and that doesn't exist. And this also doesn't work with empty strings. So the reason I have these two like with checkboxes and this with an X is my property-based test actually didn't find this, and that is because your property-based tests are only as good as your generators, right? And I forgot to generate empty strings because I thought that an empty string should not be valid as a message, right? But I wasn't actually checking that. So I wrote this. You see here, size is 1. And this is how I generate it, by the way. Like the string.printable, it gives you some string that is printable on the screen, and that is the K. And JSON is just like it recursively builds up a JSON. And this is what select looks like. That is also, I think, like it's kind of interesting. So you first create a K, and what I wanted to do is I just remove some part of this, and I add this like asterisk that says, okay, anything should be able to come here. What I did later is I switched this size to 0. So now you can generate things of size 0, but you can never use them because property tests can also get assumptions, which we call preconditions. So a precondition tells you that your test is valid or invalid. A test case that doesn't pass a precondition, so it doesn't fit your assumptions, then it is not a valid test. And hypothesis is going to tell me about this. It's going to say that 10% of your messages were invalid. They were discarded. So that means that my expectations between how this test works and my expectations of what is generated is different now. So I can actually look into it and realize why that happens. And what the obvious solution is I should never be able to construct a message object that has a 0 length key. That should be the case. I later moved to like this Redis-like serialization scheme. I have not been able to find any bugs with this. The code is open source. I'll give you a link at the end if anybody would like to play with it and find a bug and let me know. That would be great. So I would just like present it next time to somebody else. So a post-condition property that I specifically crafted, like this didn't happen by mistake, is isolation. So in such a system, one thing you really want to do is make sure nobody can leak, like the system doesn't leak some client's data to some other client, right? And how I check that is if I see a select, I look at the prefixes of the records it gives me, like the prefixes of the keys in the records. And I should only ever read my own messages if I'm running a select query as a client, right? So this, like, if you actually try it on the like demo, you can see that it gives you a bug. And the way it gives you the bug is, so imagine like, do you remember this? I think everybody remembers this, right? So imagine if we had two users, and one is a prefix of the other. One's name is a prefix of the other. And they have different objects. And the second one, Bo, runs a select query with like, I want to get everything. What happens is, because my implementation just adds this at the end of the at the end of here, so it is Bo underscore asterisk, and what this tells Python is anything that starts with Bo, you should just return it. And because Bob A also starts with Bo, I also get that. Yes?
So even if you sort of separate that into some more structured data, if I happen to ask for a key that that guesses the name of another client, then the store should refuse to give me back my data.
So what would happen is, like, what happens here is anytime store interacts with a client, to any key that they send, it prefixes their name on top of that, right? Like, so if the system was rightfully implemented, as I thought it was, then it would never be able to give me a different data because the prefix would never match on anything. Does that make sense? Not sure. I might have another bug. Like, that is always possible. Like, these things are very finicky. So the last one is a modeling property, right? Like, I talked a lot about like simple models versus complex models. And one thing you can really do, like in many, like when testing many key store examples, is have this very like simple dumb store that implements basically the same thing that you were trying to do. So you can insert something, you can delete something, and you can get something. And what should happen is if you have correctly modeled the like simple thing you have here, then your assertion should never fail. So this is the last bit of code. I'm moving away. This is how I generate my interactions. And this shows an interesting bit that it is interesting because of two things. One, I like frequency is a good, like having a weighted choice combinator for generators that allow you to bias them is very useful in a lot of cases. When you're testing real systems, you want to be able to test like different types of workloads. So tweaking these is good. And a hypothesis doesn't have it by default. They think that developers should not have that much control over their generators, so they didn't do it. I wrote one on my own, and like I think it is a nice like mind exercise if you want to think about like how I would implement this. Like there are a lot of ways to implement it. Yes.
But there you're kind of violating an invariant because your choices were two tuples, and then you are returning a third tuple in the end.
What do I do?
Yeah, you define choice as a three tuple with message, line, and choice, but on the top you have two tuples.
That's because of Python. You can do anything, right? Like you can.
Yeah, so no, that sucks. That's what I mean. So
Yeah, okay. It sucks. I did that. Like I was short of time. And I don't know a lot of Python. So we came to the end of the presentation. Now I'm going to show you 9 things that property-based testing frameworks have gotten very good in the last 20 years. So, and I didn't have a lot of time to show them in the presentation, but you should check them out if you're doing property-based testing in any shape or form. So the first is you get a lot of control when you're running these tests. You get deterministic execution. You get to replay faulty executions. Like they save like previous bugs, and they allow you to replay them, so that you don't get any regressions as you do in like as we try to model in our unit test by adding a unit test for every failing case. And so there are a lot of integrations with like existing testing frameworks, fuzzing frameworks. They have a lot of automation that I haven't shown. You can, given a type definition, derive a generator, derive a shrinker, derive a printer. So many of the things that you do could be automated. In fact, like if you ever use QuickCheck, if you have any Boolean, you can almost automatically test it. Like any function that returns a Boolean, and you think that is a property, like you think that should always be true, you can automatically test it. That is very easy with the automation QuickCheck gives you. They do a lot of like systemic exploration. They have these things that are very. Let me check on time. Okay. They have these very they have these heuristics for like starting small, then jumping to things that are known to create examples, like the bounds of a type. They generate int max, int min, so on. They give you a lot of inspection capabilities and debugging capabilities. You can get statistics about your generators. You can get statistics about your tests. You can inspect. You can add logs. You can collect stuff. You can configure them in many, many, many ways that I hadn't even thought it was possible. They do a lot of caching to prevent like running things, generating things a lot of times. And they try to do parallelization by running tests in parallel for you. Of course, they do shrinking. And recently, they also started like adding targeted PBT, where you can try to make the generator biased towards some target that you have, or coverage-guided fuzzing. So that is me. Thank you all so much for listening to me. I would also like to thank my lab mates who made the presentation much better than it was 2 weeks ago. So here, like you see, if you want to check out the repo, this is the QR code for the repo, and the slides are in this QR code too. And like if you don't trust QR codes, here are the actual links. So thank you all so much.
Thank you very much. You're pretty good in time, so we have time for questions.
First thing, thanks for doing the contest last year. And did you use property-based testing in preparing your own software for the contest?
Yes, I did.
Okay.
You mean
So,
ICFP contest, right?
Because it's a one-off, the
Yeah.
ICFP programming contest.
Yeah, I
It's
did.
a lot of fun.
So
Again,
as a
thank you.
context, like I did like not the last one, but I think I did the 3 before one, like 22 and 23. And in 22 it was a task of like, it was you were given a target image and some tools for painting an image from scratch with some cost, and you were supposed to create these instructions to paint that image. And I used property-based testing in that scenario to make sure that my implementation of the judge was actually correct. Like I had my own stuff that is like, so if you swap 2 frames twice, it should be the same thing, right? Like that is what reverse is. So yeah, I use that.
Okay.
Thank you.
There were another question. Yeah?
If one uses property pacing, or if I use hypothesis in Python a lot, I noticed that it's a very slippery slope towards very slow executions of tests. If you use it a lot and you build up more complex examples, then it gets slower and slower, and somewhere eventually it's not useful anymore because tests try to execute so long, but it's also impossible to get out of this because the test suite is so big and relies on hypothesis. Do you have some techniques how to avoid that? I haven't found so far.
Not much. But like some intuitions I have, like one thing I would do is I would try to break up tests in 2 modes. One which is like fuzzing, like bigger tests, where like they're gonna have bigger parameters. You're gonna give them longer lifetimes, and then you also have smaller tests, and you run the bigger tests in the CI, and you run the smaller test on every save. So that's what I would do probably.
Are there more questions?
Yeah, do you know of any approaches in hypothesis or any other language where the generator is influenced by the coverage of the actual program running?
Yes, so hypothesis has hypofuzz, like it is connected, like you can connect it to fuzzers. There is also there is prop test in Rust that is also, that has a libafl integration, so you can use that.
So it does a static analysis of the source code and tries to generate.
No.
No.
So what they do is AFL is very good at like generating good examples, and getting coverage information. So you run AFL in the backend, and then you just get you just trust AFL to give you the right data, because implementing that all from scratch is it's a very big effort. I don't think anybody wants to do it. Like any of the people, at least I know, wants to do it.
So they just use AFL out of the box, and that's good enough for them.
But how can you say that, okay, I now want to get more coverage, how do I change the generated input so that it really goes into that path?
So the thing you do is you can have structured mutation, right? Like if I have a binary search tree, for example, I can mutate it. It's very close to writing a generator for it. So if I have a structured mutator, then I can use AFL as my ground truth. I can ask AFL, is this an interesting path, as fuzzers do? And if it is interesting, I'm going to implement my own seed pool, like my own, what is that? Like genetic algorithm on top of it, right? Like I'm going to maintain my own seeds as Stefan does, but my data all comes from AFL. I don't try to determine if something is interesting or not, because AFL, like for our use cases, does that good enough.
Thank you.
Yeah.
Can the tools remember the random test they did once and then continue from there?
So that is a very recent thing, right? Like the mutation approach that I mentioned. That's how you do it. A generator, instead of a generator that takes a source of randomness and gives you some data, you have a mutator that takes some source of randomness, some data, and it constructs a new data based on that. So you can use this, but it is very hard to, like, generation from scratch is easier, that's one. And two is, when you're doing this, like, you need some type of feedback to do it correctly, right? So you go back into the coverage guidance, or sometimes in some domains you have these very good heuristics, then you use them, but they are very rare.
Are there more questions? Yes?
For your key value store, have you thought about testing for race conditions?
I have not, because I don't know how like multi-threading or like concurrency works in Python. Yeah, a lot of the problems, like a lot of the issues, most of them actually came from like me not knowing Python, so I did wrong things. But like that's content.
Do you know any good resources about property-based testing more complex systems? There are those talks about testing Dropbox and stuff.
Not much. So like there is this recent trend where like deterministic simulation testing, like and in the antithesis style or like Tiger Beetle style is very much popular. I think they are doing something that is like in spirit very close to property-based testing, and like they are the most complex examples that you could probably see like out there. Like researchers have done a lot of those things. Like John Hughes tested, I think, Volvo cars and like some very complex systems, but a lot of the stuff is unknown. I don't think there are any good resources.
I also would like to question whether applying property-based testing to large systems is a good fit, because all it does is randomly generating data and hitting, I mean, if that system is very buggy, maybe you will find something, but if it generally runs stable, then hitting interesting edge cases by randomly sampling something is very unlikely. And in these cases, I think it's, for big systems, I think it's better to actually go back and think about the interesting inputs rather than relying on having them found randomly.
I agree with that, like to some part. Like one counterexample, I am currently working on testing an SQLite port to Rust, which like there are numerous bugs I found. But more importantly, the researcher that I have been modeling, basically, his name is like Manuel Rigger. He's from Singapore, and he has found over, I think, 400 bugs in like very prominent database systems like SQLite, MySQL, DuckDB, HDB, a lot of those things, by going one more step than the fuzzer and trying to find logic bugs by random generation. So I think there's a lot of like potential too, if it's done correctly.